Alright, so we have been taking the what's called first derivative of everything. Okay, we've just been calling it the derivative. Okay. However, we can take multiple derivatives of something, and those are considered our higher order derivatives. So I can take the second derivative, the third derivative, the nth derivative. Okay. Basically, I just keep adding tick marks up until I get to like 4. After that, you're just gonna write whatever number it is. Okay, you don't want to have like 7 tick marks, right? It just starts getting confusing at that point.
Oh, this is really on.
Okay, likewise, we can kind of write them as derivatives. We're going to look at it kind of like an exponent next to your d's. Does that make sense? Okay, and then you don't really see this last notation very often. But yes, so basically you're just taking the derivative, bless you, of the derivative. Are you with me?
Oh.
So the process.
equation?
What?
Same equation?
Yeah, same power rule, product rule, quotient rule, all of that stuff still applies. I'm just taking the derivative
It's
of
just
the derivative.
a new equation
Yeah,
that you are making.
Correct.
Solved.
Okay. Let's look at it
Well,
again.
I guess do this.
Alright. So this says, because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these falling things is s of t, which equals negative 0.81 t squared plus 2. Why is this number different than what we're used to dealing with? The gravity is different.
Okay.
So that normal number we see is usually 16. Yes?
Yes.
Normally we have a 16 in front of our t squared for our position function, right?
Yes.
And that's because the gravity of the Earth is negative 16 versus on the moon,
I forgot we went below.
it's in a different unit.
Okay.
Yeah, so it's negative 16 feet per
Feet,
second.
feet per second, it's negative 9.8 for meters per second.
Okay.
Yeah.
Oh,
Depends on your
okay.
unit.
That makes a lot more sense.
We usually use feet in mathematics, we use meters in science. And it is 16 is rounded. We round so that it's a nice number.
Okay.
That's good.
Alright, so anyway, this is where S of t is the height in meters and t is the time in seconds as shown in the figure. What is the ratio of the Earth's gravitational force to the moon? What is it asking us to do? I don't know. Okay, that's a good answer.
So you need
Well,
the Earth's gravitation. I'm thinking of this in physics brain.
Okay.
Same.
So, what did we just talk about? What is our gravitational force for Earth? Negative 16, and we said that's in what? Feet, okay. And this time they do give it to us in meters. So what is it in meters? Negative 9.8 meters per second. Agreed?
Yes.
Agreed.
So nice.
Now, if I think about what it means by gravitational force, yes? It's a force acting on objects. Agreed? Okay. So let's think about that, what that means in terms of our position function. Okay. So if I take the derivative of my position function, okay, what do I get? You should know. Yes, but what is the slope? What is the derivative of our position function?
H2.
Which is called what?
Instantaneous
I even watched the
Velocity. Okay, right? So if I have s of t, this is my position function. Okay? If I take the derivative of that, that also equals v of t, which is our velocity function. Basically, velocity is the rate of change of your position. Agreed? Let's think about that going a step further. What would we get if we took the derivative of velocity? Acceleration. Which is also going to be what? The rate of change, okay? What's another word for it in context of this problem?
Second derivative?
The second derivative of our position function.
Talk about the
Agreed.
ratio.
Yes, but what else?
How fast the thing is accelerating. This is still think it's bringing me. So
Correct. It's how fast it's accelerating down.
as it's
Yes.
falling.
As it's falling, okay? Which is going to be due to the what?
Force of gravity.
So, your acceleration is going to be your gravitational force.
Yeah.
Are we with me?
Yes.
Or solid acceleration, but if it's negative, that means that we're going down, okay? So, I know what it is for Earth, right? It's negative 9.8. Agreed? Okay. How would I find that then for my moon?
You take the derivative of that.
I need to take the second derivative of that. But we can't just go from our position function to the second derivative. What do we have to do first? Take the first derivative. Okay. So my first derivative of s of t is going to equal what?
Negative 1.62 t.
Negative 0. What?
Oh, I got 1.
1.6.
Yeah. T.
And that's it.
Okay. Agreed. Alright. And then, so that would be my velocity function. If I want to know the acceleration of that, what would I do? Take the derivative again. So this would be my second derivative, which is also my acceleration. And what do we get? 1.62. Okay? And if they ask us for the ratio of those two things, what am I doing? Put one over the other one. Agreed. But which one goes on top?
Earth.
Why?
Because it says Earth first.
Correct. So I'd have negative 9.8 divided by negative 1.62, which gives us what?
Somebody do that. I don't know.
Point
0.49.
6.049. And what's my unit there?
Meters per second squared.
Just
Is it?
Isn't it? That's
They're just
acceleration.
numbers.
That's the units for
meters,
acceleration.
inches.
Acceleration.
So each one of these would be in what? Okay, but if I have meters per second squared over meters per
Nothing.
second squared, I don't have a unit.
That is
Okay, because I'm talking about a ratio of those two things, basically we're saying that it's going to be 6 times the amount of gravity from one to the other. Does that make sense?
Which is why on the moon you can go boing.
Yes. Because you have 6 times less the amount of gravity than on the Earth. Alright,
When you come back in space, you're
so let's look at another one. It says the velocity of an object in meters per second is v of t equals 36 minus t squared. Find the velocity and acceleration of the object when t is equal to 3. What can be said about the speed of object, of the object, when the velocity and acceleration have opposite signs?
slowing down.
Yes.
Yeah.
We'll get there in a second. Alright, so what do we need to do? They give us a velocity function,
Get that acceleration.
okay? get the acceleration. How do I find acceleration based on a velocity function? Take the derivative. And this is the derivative of a derivative, right? Because this would be the derivative of my position function.
Yeah.
So a of t is going to equal v prime of t, which would be what?
Negative 2t.
And then they specifically ask us for what?
The velocity 1 t.
3.
Oh,
Okay.
oh,
So I would get 36 minus
No.
9, which gives us
27.
Yeah.
27, and we're in meters per second. So then my a of 3 would be
Negative 6 negative 6 meters per second squared.
okay. So then they ask us, okay, what does it mean if those two things are opposite signs? So if we think about it, okay, our velocity or our speed, okay, is positive, or in other words, the change in our position. However, acceleration is the change in the velocity, okay? So if I have a positive speed, but my change in that speed is negative, what would be happening?
You're still moving up, but you're slowing down.
Correct. So it would be slowing down. Okay? What if it was opposite though? What if I had a negative velocity? Then which direction am I moving?
Backwards.
Okay, backwards. Okay? But I had a positive acceleration.
Means you're going speedier backwards.
Faster backwards.
You're slowing
We're
down.
So I'm still slowing down, right? Because they're still opposite signs. So if velocity was negative,
Always gonna be.
if velocity is negative but acceleration is positive, right? They're still slowing down. Now, if velocity is positive and acceleration is positive, then I'm speeding up. And if they were both negative,
Speedy.
I'm speeding up.
Right.
Dang.
Same
Does your
simple
velocity-
facts.
Same simple fast. Okay.
Would you eventually hit 0 and then start speeding up?
Yes.
Depends on the function.
Okay.
Because he's from the
Like in
future,
this
so he's already
simulation
moving
situation.
backwards.
Alright.
Okay.
Let's look at one last example.
Love that.
What? So I have. We looked at a little bit of something like this in my homework, okay? But they were just like line segments. So this one's a little bit different because it's a curvy line. Yeah.
That's a.
It could be. We don't know what it is.
Could also.
Could be. Okay. So if that's F, agreed? They want us to graph two things. They want us to graph our F prime and our F double prime. Okay.
Yeah.
Which means our second derivative. Now again, remind me, what is a derivative?
So it's
Slope of the tangent line. Okay. So let's just start by graphing our F prime. Now, the easiest place to start, okay, for our tangent lines is going to be anywhere that I have a horizontal tangent, okay? Because what is my slope of a horizontal tangent?
0.
0. So that means that at 0, I am 0.
Oy.
At, say, pi, so let's just use the same labels for consistency's sake. So this is pi, this is 2 pi. We with me?
Here.
So it would also be 0 here, and we're also 0 here. Agreed?
Yes.
Okay.
Then we have to think about, okay, what type of tangent lines do I have here?
Oh, you want
Negative.
They're negative. Agreed? So between 0 and pi, I have negative tangent lines. Agreed? So if my f prime is the slope of the tangent line, my tangent line is negative, where is it going to have to be?
Down.
What do you mean by down?
Below the X.
Below the x-axis. Yes. So I'd have something like that. Okay. Then, as I turn and go up, what type of tangent lines do I have here? Positive. So it has to be
Low.
Above the X.
Above the x-axis. But we know eventually it has to come back down. Yes, because it has to hit 0 at 2 pi.
Yeah.
Agreed?
Yes.
So, my orange graph would be my f prime.
Okay.
So then what do we want to do from there?
Graph that and do the same thing you did with the last one.
Okay, find the next one. Okay, so again, I'm translating. What do I want to find first?
Where is 0?
Where what is 0?
And tan.
The tangent line slope is 0. Okay, so that would be here and here this time, roughly. Agreed? Because that would be my tangent line.
Mm-hmm.
Okay, so now from 0 to pi over 2, what type of slope do we have?
Down.
Negative. Okay, and then between this we have positive, right? So we would be going like that.
Okay.
Yeah.
Okay. Do I continue going up?
No.
When do I need to come back down?
And that
There.
part. Yeah.
Okay. And then after this point, we have a negative.
Yeah.
Ah.
So that would be
Okay.
my f double. So
Wait.
you want to start with your horizontal tangents and then look at where is my slope positive, where is my slope negative, and that's what you're going to graph.
It looks like DNA.
Hey,